So what we want to think about for power series is we really want to imagine them being like a geometric series. So the first power series would be centered at basically like x equals 0, whereas the second one, just like a Taylor series, would be centered at x equals c. So one of the things we have to remember for a geometric series, if we have something in this form, is we can set it equal to the sum of a geometric series, which is really our a term, which is our initial value, over 1 minus r. So that's kind of what we want to think. But this is going to converge if the value of r is less than or equal to, is less than 1. It can't equal 1. So as long as it's less than 1, we're good. If it ends up being equal to 1, then we're just adding in a whole bunch of times. So that's the main thing that we got to be careful about, is making sure that our radius is equal to 1. Now, when we do these problems, we're going to find out that there's 3 different forms for the radius and interval of convergence. We can have a radius where it equals some sort of number, and so then our interval of convergence is going to be from one number to another number. We can have a radius of 0, and then that really talks about no interval convergence. And we can also have a radius of all real numbers, where it doesn't matter what you have for r, because we have something to the n. We have an infinite radius of convergence. And so then our interval convergence is all real numbers. Now, this will make a little bit more sense when we actually see them in action. So, a couple things we got to be careful about. We need this radius to be less than 1. Now, sometimes that happens for a certain number of values. R could be like 0.5, then our radius would be around 0.5. But as these power series get more complicated, we start getting different options here. So let's see what that looks like. So we want to find the radius and interval of convergence for the following series. Now, we first have to recognize what it is. So our a sub n is basically 1, and then our r is our 2x. So what we need is the absolute value of r, or of 2x, to be less than 1. If this is true, then it converges. So we basically have to solve this now. We can just divide both sides by 2. So we have the absolute value of x has to be less than 1/2. So what this ends up being is our radius convergence is 1/2. Well, where's this centered at? Well, this could be a little bit more obvious where things are centered, like for this problem down here, it's going to be centered at 4. Think about your Taylor series versus your Maclaurin series. So like a Maclaurin series, this doesn't have any plus or minus a number. So this one is centered at x equals 0. So now, I have a radius of 1/2, and we're centered at 0. So if I was to draw a number line out, I would put 0 in the middle, and I would go 1/2 to the right, and 1/2 to the left. All right, now one of the things we got to be careful about is, if we did like the ratio test, we might be able to see this, but what happens at one of the endpoints? Now, you're going to find that some of these problems are going to converge at an endpoint and diverge at a different endpoint. So what we have to do is we've got to plug in our endpoints and see what we get. Now, usually this is not such a tough thing to do. So if I was to plug in 1/2, my one endpoint here on the right, into the equation for x, we get 2 times 1/2 to the n. Nope. All of this raised to the n. And we're doing an infinite number of those. Well, the sum of 1 to the n is 1 plus 1 plus 1 plus 1. It's going to diverge. So at 1/2, we're going to put our parentheses. All right, so let's see what happens if I use the negative 1/2. So get the sum of 2 times negative 1/2 to the n. All right, now this looks a little bit more promising. It's negative 1 to the n. Well, that's an alternating series. This will converge if the whole series goes to 0. However, there's no other part of it. It's just going to alternate. So sometimes it's going to be negative 1, sometimes it's going to add back to 0, sometimes it's going to go back to negative 1, etc., etc. It's not going to converge. So from negative 1/2 to 1/2, we have parentheses on both because we can't use either. So our basic steps are we figure out where we're centered at 0. We set the r value. The absolute value of that has to be less than or equal to 1. Not equal to, just less than 1. And then we figure out what x has to be. We don't do the whole absolute value inequality deal where we split it up into two equations like you might have done in the AT. It's just solve for x. So let's see that in the next problem. So the first thing we got to do is we have to figure out what's our a term and what's our r term. So what we can do is we really can pull all of this inside one r value. So we got the sum of negative 1 over 2x to the n. Bring everything inside. So now we want the absolute value of negative 1 over 2x to be less than 1, because that's my radius. I could have the a's out front if I want to, but really whatever's raised to the m power, that's my r. Okay, so the negative part doesn't make any difference. Oh, so we're just going to multiply both sides by 2 over 1, the reciprocal. So we get the absolute value takes care of the negative. We got the absolute value of x. It has to be less than 2. 2 is my radius. Sometimes it just asks for the radius of convergence. So if it says radius, the radius is 2. It's not less than 2. It's just whatever that number is. So on the number line, we've got no plus or minus. So my number in the middle is 0, but the radius is 2. So we go 2 to the right, 2 to the left. And now we've got to check our endpoints. Now, if I plug in 2, I end up getting the 2.5 to cancel out, and I get negative 1 to the n, which just like we saw here, doesn't converge. If I plug in negative 2, I get positive 1 to the n, which also doesn't converge. So my endpoints are just parentheses negative 2 to 2.
So when you get a power series and you're not really sure what you should be doing with it, you can't tell what's R and what's A, and you just kind of want to figure out what it should be. One of the main things you can do is use the ratio test. And I mean, that's true of any series, especially if there's a factorial in it. Ratio test is generally a pretty good thing to use. So I've already actually set up the ratio test, which just means you use your next term, so n plus 1 factorial, x minus 4 to the n plus 1. Now notice it's not x plus 1, but just n plus 1. When you do the ratio test, you're plugging in n plus 1 for all of the n's. Over 3 to the n plus 1 times the reciprocal of what we started with, because we're dividing it by the original. So the 3 to the n comes up to the top, everything else comes to the bottom. Now, the first thing we can do is either not write it in the first place, or just cross off the negative 1s to anything because we're taking the absolute value. So regardless of what that comes out, they kind of cancel out. Alright, other things that cancel out pretty easily. 3 to the n cancels with 3 to the n, leaving us with 3 to the first on the bottom. So let's just put that down here. 3 to the first, or just 3. And then our n plus 1 factorial and n factorial is going to leave us just with the n plus 1. So that part is gone. And then we have an x minus 4 to the n that cancels out, leaving us with an x minus 4 on the top. So we want this limit as it goes to infinity. We really want it to be less than 1. Well, let's think about this. We're taking n to infinity. Now, it really doesn't matter what x is. We have this n plus 1 on the top here. Well, let's think back to the original problem. We've got n factorial, which is pretty darn large. X minus 4 to the n. I mean, as soon as x becomes larger than, say, 7, this ends up being 3 to the n over 3 to the n, basically canceling out. Anything larger than that, and it's going to go away anyway. And then we're multiplying by some huge number. This is not going to converge very easily. So thinking about this limit's not going to be less than 1 at all, really. As long as n's going to infinity, you've got infinity times x minus 4 over 3. There's only one situation where this is going to be less than 1, and that's when x equals 4. Because that will end up giving us something times 0. Basically, every single term would be 0. And that's something that approaches 0 when you talk about L'Hopital's rule, infinity times 0, if you're talking about both of them approaching, you don't know, that's indeterminate. But we've got everything that's times 0. So our radius is really just 0, and it only happens when x equals 4. So this is the point where if you're looking at the number line, you've got 4 in the number line, and it's just 4. So it's not from something to something else. The radius is 0, and the interval convergence is just x equals 4, not 3 to 5, just 4 itself. All right, so let's try that same trick with this next one. We don't know what to do, so we're going to use the ratio test. So n plus 1 factorial x to the n plus 1 over, now we got to be a little careful here. This is not 2 times n factorial, it's 2n factorial. So 2 times n plus 1, all of that factorial. So that's a little bit tricky because you got to distribute the 2 into the n plus 1 times the original, and the reciprocal, 2n factorial in parentheses, divided by n factorial x to the n. All right, let's do with the easy parts first. The x to the n's, all you're left with is an x on the top. The n plus 1 factorial and the n factorial. The factorials basically cancel out. You get the n plus 1. All right, so we got that up there. And now, here we got to be a little more careful. This is 2n plus 2 times 2n plus 1 times 2n factorial. That's really what this 2n plus 1 factorial is, because it's 2n plus 2 to the factorial, which is 2n plus 2 times 2n plus 1 times 2n minus 1, etc., etc., etc. Now the 2n factorials cancel, but on the bottom we're left with a 2n plus 2 times a 2n plus 1. When we're looking for this limit as n goes to infinity, we want it to be less than 1. Well, let's think about this. X is a number. Some number could be really, really large, but it's times something to the first divided by, if you were to FOIL that out, something squared, n over n squared. If you take the limit as n goes to infinity, the degree is going to be larger on the bottom than it is on the top, and it's going to go to 0. So it does not matter what x is. It's going to converge no matter what x is, because n is going to go to 0. The limit of this function is going to go to 0 as n gets very large. So in this case, the radius is going to be infinity, and our interval convergence is going to go from negative infinity to infinity, or all real numbers. So this has an infinite radius. It doesn't matter what x is. This is going to converge for every single n. Now, thinking about that logically, we got some x to the n power on top. It's a large numerator, but we find that factorials are even larger. So, at least in this case, because it's x that's being raised to some n power. So n factorial over 2n factorial ends up that 2n factorial is so much larger. And n can be such a larger number than x that this x to the n thing is not really, it's not powerful enough to make this drop out. Now usually, like, n to the n is huge. It's a lot bigger than n factorial, because think about this. If it was 1,000, this would be 1,000 times 1,000, 1,000 times. Whereas over here, it'd be 1,000 times 999 times 998 times 997, etc., etc., etc. But since it's x, and x is not running off to infinity, that's why this doesn't really get as large as you might think it would. All right, so in the end, a radius of convergence is whatever would make the inside of this less than 1. And we got 3 options. It could either be that there is no radius, and it's just the point, wherever x is centered. And the number 7 here, x would be centered at 0. This one's centered at 4, just like in the Taylor series. You always have x minus the center. It could be that it's all real numbers, or it could be that it's some sort of interval, like 4 and 5. But if it is an interval, you have to check your endpoints, which is the least, at least my least favorite part of the game. So you got to check your endpoints. These two, they were kind of tough with the ratio test and all, But when I don't have to check the endpoints, it makes my life a whole lot easier.